Good evening, everybody. Thank you for coming. I'm Michael Walker with the Data Science Association, and we have a wonderful event tonight. We have Tom Flaherty, a good friend and colleague of mine, who's an old Scala hand, and we can all learn a tremendous amount from Tom about Scala, which is really a cool language if you haven't seen it or had a chance to play with it. We also have Donnie Yancey, who's the COO of MapQuest, and Donnie is going to be presenting on location intelligence. A few house cleaning items. Next month, we are going to have an event on Spark GraphX, and the presenter will be our own Michael Malik, who just did a wonderful presentation at the Spark Summit in San Francisco, albeit on a different subject. Mike is writing a book on GraphX for Spark, so he really is the expert in this area. And I think, where will that be, Mike?
Galvanized Platte River. Actually, over here in Lowhigh, I think, galvanized.
Delaware.
Yeah,
no, that's right, we changed it.
Yeah, we changed it. So anyway, we'll send out a notice. I think it'll be June 14th. And then that's July 14th, excuse me. And then August 11th, we're going to partner up with the University of Colorado Boulder High Performance Computing Conference, and that should be fantastic. Then sometime in September at Walker Art Gallery, we are going to have a big party, and we're going to get all the other data meetups in Colorado to partner with us, and we're going to have a great party in September. Anyway, I'd like to turn it over to Donnie. He's going to say a few words about MapQuest, and then we'll turn it over to Tom. Thank you.
Thank you, Michael. Hi, everybody. I don't want to sound, I don't like standing behind podiums. I don't want a mic in my hand. You guys have probably known MapQuest for a long time, right? We're still around. We're still thriving. We have 40 million plus users on a monthly basis that use MapQuest. That is more than Apple, actually, in terms of my iPhone perspective. Not anywhere close to Google, but we understand why. But that's more than what Bing does, as well as Yahoo Maps. So, MapQuest has been around for a long time. We obviously use data. We're in the location game. One of the things I will talk about, in a bit, one of my presentations is about kind of that data as a service element. It's not about just using data to help, improve your business, improve performance. It's also about how you can take data and make it a product, and how can you make that a solution to sell in the open marketplace. So in that aspect, I will let Tom speak first, but I will also give the the caveat there. Because of this, data as a service business we're building, we are looking to hire. So these are people anywhere from data scientists, data engineers, business analytics, operation analysts. So definitely, if you are interested in learning more, talk to myself. Mr. Hernandez here will be around to help as well, and kind of go from there. Awesome. Thanks, guys, for coming out. And Tom, there you go.
Okay, so for about the next hour, I'm going to go on about all the nice things about Scala, but with a real data science perspective on it. So why is it good for data science? Well, I've been the chief architect for 20 years, first started in Scala in 2008, did a symbolic math thing, which I eventually did for molecular dynamics at Glaxo in 2008. And then later on, when new languages on the JVM were all new, exciting, like Scala, Clojure, JRuby, and Ruby, we formed a Polyglot panel and went up and gave talks in Denver, Boulder, and Colorado Springs. Okay, so right now I'm working on doing some analysis for enterprise architecture practice, how information flows with a little bit of instructional theory. So yeah, Scala's really gotten popular. Of course, we've got Spark, which can do most anything, including replace most of Hey-Do. Cassandra has come to life now with the new Spark connector. I highly recommend trying it because it really has an affinity for Spark and RDDs. And Kafka, which is now our new high-speed messaging system. So Scala is really playing a big role now in our ecosystem, and it's good to get to know it. Obviously, in some situations, you can use Java and other languages, but Scala usually gets you to the heart of the problem, and we'll see why. Okay, so what's its success factors for data science? Well, we'll get to the affinity with data, state-of-the-art OO for class composition. In fact, it even lets you do multiple inheritance, and I'll show a little bit of that. Functional programming with streaming, which for data science, functional programming gets kind of close to mathematics. Initially, it looks pretty cryptic, but you can make it look mathematical. In fact, we'll do that. Also, concurrency under the covers. Spark, practically don't have to do it. It takes care of itself. That might be a strong statement, but at least starting out, Spark will take care of you. I've said that Scala is probably the fire-breathing dragon in the cloud with Akka. If you have a multi-core processor, Scala will probably, and Akka, keep it busier than any other platform. The Spark ecosystem, which will get covered again. And finally, a vibrant open source community. Spark is now the most active, that sounds different, most active project in Apache with almost between 300 and 400 committers. So it's going to be, these are going to be around for a long time. It's not just a flash in the pan. Okay, about Scala. Really, it's the true hybrid of OO and functional programming. In my book, I think it's got the best OO and very good functional programming. Actually, I like list and closure a little bit better, but the Scala functional programming in Scala is quite powerful. It really leverages the JVM. We get to the concurrency with Dudley, who did the concurrency for Java 5, and then he's consulting with typespace to improve it. So some of the things we see in Spark has its origins with that, but just-in-time compilation, well, why should you really worry about it? Well, a lot of times when you're doing a declarative high-level language, you put a lot of little junk in the code. The code compiler puts a lot of little things, and which in some situations can slow down performance. But the JVM has been around so long, in fact, it's probably the most mature server environment, that it optimizes out a lot of this stuff. And that's powerful. So consequently, Scala, which produces lots of little nitpicky things, its speed is plus or minus Java, 3%, which means it's really the same speed as Java. And it's strongly typed, and we'll see what that means shortly here. Fully interoperates with Java. I mean, there's nothing you can't do that you can do in Java that you can't do in Scala. Okay, so now we're going to kind of say, we're going to ask data first what it likes. Nobody's ever done this in data science, so I think it's long overdue. And then we'll ask what data scientists like. And then finally, we'll go into some Spark and some RDD workflows. So that's the general outline for tonight, in about 50 minutes. Okay. Has nobody ever asked data what it likes? Anybody in this room? Okay. Well, we're going to change that. First of all, it likes to declare itself. It just likes to be seen. It likes to assert its identity. And we'll see where Scala's showing typing makes that work. It wants to be a first-class citizen. It doesn't want to be a little primitive. It wants to be way up in the hierarchy. Finally, it wants to remain intact. Mutability is really a mess with data. In fact, it should never have happened in the first place. It likes to be wrapped. And in being wrapped, we're going to find, it's going to produce whole new meaning and everything. Wrapping is a very powerful concept. It wants to elevate its station in life. We're going to lift it to another playing with existence, i.e. mathematics. It likes to reveal itself. Pattern matching, we'll see how that works. And finally, how some really powerful ways where data can share its contents. So let's see if Scala makes data happy. Okay, first of all, so I said Scala is really going to by the way, can everyone read the code here? I got it up to about 24.5. Okay, it's kind of iffy. Yeah, part of the thing is I'm in this like inner sanctum or something there, but we have to stand here for the video camera. Okay, well I'll try to then walk you through it. So really the first thing Scala has is a trait, which is just a nice little thing that you can mix in anywhere. Think of it as you have a stew, you have a main thing in there, and traits are like the ingredients that you can add into them. And you can mix and match like crazy. In fact, the Scala compiler itself uses traits like crazy. A lot of times you just run an abstract class, which then you can expand with traits. You have a concrete class, which is instantiated by itself. Case classes, which we'll talk about in greater detail. And then here's where the multiple inheritance comes in. And we'll see an example of this. So you start off with a base class, like main ingredient, and then you just throw in the seasonings. And then you throw them in pretty randomly. The order you put them in is very important. But maybe that you have a lot of freedom. You don't necessarily have to do it during declaration. You can do it during construction. So you can, at the last minute, add that magic ingredient in there. And then Scala has something, they call it object, which is not maybe the best name. But the first one you see here is a singleton. It's just a reference point where to find things. In fact, a lot of Spark code starts with a singleton object. And then other times it has a companion object, which in this case you can use it to construct new classes, like the new operator here. Or so we can get back, a whole set of factory methods. And then this thing called unimply, which is a way of sharing data. And we'll see how that works in a couple more slides. Okay, asserting identity with strong typing. Well, if you look, when I look at this and I see everything in yellow, I get goosebumps. For the simple reason that with all these type declarations, I can tell you real quickly that I can tell the compiler to assert correctness. I can also say that working this way can cut your unit test down by a half or even smaller. One of the important things here is to get a sense of what this notation is, the parametric type, where it's really saying these are all collections or sequences. It's really saying it can hold anything. But we're going to tell it the last minute or have it figure out what it can hold. So this is the parametric type right there. Okay, by the way, we're going to revisit these functions back in Apache Spark. So these are the usual things. So now, we'll take any kind of collection, apply a function, treat, and actually we'll say, by the way, I should point out, all the types start out as T. And then we change the type from T to U in the last minute. And we even tell what function that is. So what map does is takes a sequence, T, and transforms it to a sequence U. And it can be just about any kind of function. By the way, this notation here are what's called a functional closure. And very often can be, depending on the type of collection, can very often single or it can be multiple arguments. Down here, our functions are saying, or inserting some kind of truisms. In this case, filter. We like to say, okay, we only want things here. Like down here in the example, we want to say, okay, we have a list of 1, 2, and 3. We only want the odd numbers, and we get a list of 1 and 3 back in there. And again, very simple one-line operation. Another thing that's important is, in all these situations, is we're actually creating new sequences, new lists. We're not changing anything, we're always creating new things. And this is beginning to see what immutability is all about. So, flat map. How many people have seen flat map and don't know what the hell it is? Okay. Well, flat map is like map, except in Summon, he's taking a single value and kicking it out to multiple values. Like, for example, being a line, he'll create a sequence of words, and we'll see this later on. And then after, you give him a bunch of lines, he creates a bunch of words, but then he takes away, he flattens out all the collections that you dumped into him in there, and gives you just one big flattened sequence. And so we talked about filter. Exists assertion, we can assert whether something is in there, or whether everything, fits the criteria, whatever. And reduce it looks a lot like the reduce in map reduce. It will take two subsequent values and actually apply a function and do things. Very often you apply a summation thing or an add operation, that's a summation. Then you ask, hold it, he's always asking for two values. How does he get started? Well, all these classes have a concept of zero. They have 0 for ints, 0 for floats, but the concept of 0 can even extend to strings. So a blank string is actually a starting point, or you can say the 0. Officially, it's called a monadic 0, but we won't get into that tonight. In there. So we'll see a lot of reduce. But this crazy function will play it's going to play a big role in a lot of the map and reduce operations because he's summarizing everything. So these are your building blocks. There's probably another 50 methods in sync in there. But these are the ones you're going to see all the time. Okay, next slide. So we have now allowed data to assert itself. And in the process, we're telling the compiler how to be correct. Next phase, class. Let's move ahead here. Hit the wrong button. Okay, data as a first-class citizen. What does that mean? Well, it means he can be an object. Now, this doesn't look like much, but I can tell you it's a very profound concept because if you look at Java, Java comes in here and says, okay, this is where I'm going to start my base Java object. Scala says, no, hold it. You don't know what to do, really know what to do with the primitives. When I say primitives, I'm saying double float in that. So Scala made an any value, and then he took the any value and then he wrapped it and he done subtypes of any. Now we have a fully generalized object hierarchy. Other things we see a lot, strings are, just like a Java string, the Java classes, and then we start the rest of the Java classes. And this is seek and list that we saw in the previous slides. That's where they belong. Option is a better replacement for null, where we say there's something in there, but it's something not. Very often if we wrap something, we like to know if there's something in there or not, but that's all we care about. By the way, Scala options use the matching. Scala null, which should be avoided because nulls are like throwing hand grenades into your code. But it's in here for Java compatibility. And the concept of nothing. And nothing, anything, can be assigned to nothing. We actually have this concept of a vacuum or empty space. So what this all is about? Well, you can take the number 5, Scala sees it, the compiler sees it as an object, and say toString in there. And there's a host of methods that you can run in these primitives. Another thing which we can't show here, but if you put primitives into other classes, Java had a way of doing all-boxing. So it was always trying to do these weird things to deal with things that weren't in its class hierarchy. Scala doesn't do it. It doesn't have to. Okay, so data is now a first-class citizen. We can treat it with all kinds of powerful concepts. Okay, mention the mutability. Well, where should I go? Well, first of all, mutability really means that sometimes if you think of data, if you're running a data warehouse, you don't really change the data. You don't have to just archive it and maintain a historical record. So in some ways, it's along those lines. If you ever thought in parallel, if you decide that, you set this parallel thing up, and then at the last minute you change your data, there's no way to tell the system how to deal with that. People have tried with lots of mutexes, but they never come out into a final consistent way. Also, what's interesting, when something's immutable, you can send it anywhere. He's not going to get messed up or destroyed or changed or anything. So immutability promotes sharing. And then I come back and say, you can hear already I'm a fan of OO, but I'm not a fan of OO encapsulation. It was a joke. It was a bad place to go. I mean, it's the root of all evil sometimes. The set method is the enemy. Do not mutate state. Scala does have some new classes and collection things, but again, that's more for Java compatibility. They're not really used in the mainstream anymore. Okay, and another thing, public, private, protected, really not necessary. You think about how data should be shared. And then I'd like to say that data that is owned and encapsulated slowly dies. Data that is shared and allowed to flow is living, breathing data. Okay, data likes to be wrapped. Okay, what is going on here? Well, this is the case. This is actually how Scala, when you go case class, this is what he does. He says, well, first of all, with val, he says the contents are going to be immutable. He's going to give you a really powerful equals, which actually works on the whole thing, and it's actually recursive. And finally, he's going to give you a companion object with apply, which is a quick and dirty constructor, and multiply, which actually takes the data and sends it forward. And we'll see how that works just a little bit later here. Okay, now a little bit, step back for a second. I'm going to say, okay, I'm going to show you how case classes can be used for mathematics. And what I'm doing is a classic abstract syntax tree. I'm taking this statement here with a multiply and two adds, and that's the way it looks like in the tree. Okay, so this is the fundamentals. So what we're going to do is now apply mathematics. Do some hard mathematics in about the next 3 or 4 slides. Okay, but treating that. Okay, first of all, how do we elevate all our things? And we'll get to this expression in the next slide. How do we create the bare bones of it? We create these classes. So in a way you could say num is like a mathematical num, and strings become variables. And those are actually the things. We actually do our own parentheses, and negation, power, multiply. Now to think about it, this is only the start of symbolic maps. You can have the trig functions, you can have log functions. In one case, piece of code that got up to 47 things. But for now, we're going to keep it out to about 9 different case classes. So all we're doing is wrapping mathematical expressions. Well, let's see what this is, where this is going. In there. Okay, what does the core mathematics expression look like? Okay, well, first of all, we're going to say when you find a number, or when you find an integer, you wrap them with an m. So I'm a double string. So, and by the way, I should put in implicit are a beautiful concept in Scala that says when you go find something cool, convert it to something else. On the other hand, implicit should be used very, very gingerly, or they should be kept in scope. Okay, Scala has another property. Operators are actual methods. So we can actually declare them as methods. So what he's saying is if you find, these are binary operations with a this, which you could say is you. So if you find the power thing, wrap it in a power case class. And the same with all the other division multiplication multiplication, subtraction, and addition. And then we even have a special construct with a single argument for negation. What are we doing here? We're taking the operators that we see in the normal language and putting them into a symbolic math world. Okay, where is this going? Okay, well, we can actually do differentiation symbolically. So, the differential of a number is 0. The differential of a variable is just, things that we say x becomes dx. We can put parentheses around it. We can negate. We can do the multiplication law, where you can say it's the power of u, v. We bring v over, and we subtract 1 from u. Now this is looking a little cryptic, so bear with me. Okay, it's going to look better on the next slide here. Well, we're beginning to do symbolic mathematics. And look at how much code it is. It's like 15 lines of code we're starting to do differentiation in mathematics. Okay, now, remember those overloaded operators from before? So let's apply them. So now it's beginning to look like your calculus. And I should point out something I didn't do on the previous slide. It's probably better to do in this slide. This is, remember, it's a tree. It's recursive. So every time we say take the differential of things, we also say whatever expression was there, you recurse down the tree, and you keep going on and producing all this. Anybody remember the chain rule? It's recursive. And this is the manifestation of it. So, anybody can see these formulas from you, like VDU plus UDV? Okay, well, you can go to a mathematics or a calculus textbook and start translating it to Scala. Okay, so we are now working in symbolic mathematics. So really now, and then what I'm saying finally about data is data has been raised to a higher level of existence. And there's no higher level of existence, at least if you're a math major, than that. Maybe some people disagree, doing other things, but that's my opinion. Okay. Okay, now we're going to change gears. We make data happy. Now the real job is to make data scientists happy. Well, first of all, I was looking at my pharmaceutical work, the scientists. They love looking at data, but they didn't like, having to maneuver around and change it. They wanted the universal data representation. This was 1990, and I said, no, can't do it yet. Gotta wait. Also, a scientist could take care of their data, so actually, they gave me a pager, and at one point, their data, at 12 o'clock at night, So I really wanted something that was location intelligent in there. So many things all at once. Well, we're getting the sense that things like immutability and other stuff, and living in the cloud, like who really wants, if you're really at data science, do it really manage the cloud directly? And the answer is no. So my contention is Scala plus Sparks manages some very complex things. We'll see a few illustrated examples on it. And really, you want to orchestrate your processing. Well, it helps to have a universal data representation because you don't have to orchestrate the conversions. So it helps to have these Spark streams. And then streams in general. Okay. So, everyone's seen the old Apache Spark slide. It's time to jazz it up and say, what's Spark's really about? What's the cool stuff in there? Well, first of all, almost all your code talks the Spark tree RDDs. What is an RDD? Well, that's a universal data representation, but we'll cover this in greater detail. And then I can say that, you mentioned that the best viewing now is coming from Kafka. Some of the most incredible work is the machine learning library and things. We thought that this machine learning could actually be done in streams, And then finally, because Scala is now becoming the database of choice. Does anybody ever heard the CAP theorem, by the way? Or we talk about availability and consistency and partition tolerance? Okay, well, interestingly, it's like a triangle that says you can have two. You can only have 2 out of 3 things. So Cassandra is actually high on availability and extremely high on, running on particular nodes and clusters. He's a little slow in consistency, meaning that if someone was to enter a lot of data into Cassandra and you were to query it right away, you may not get exactly what they got right away. It becomes eventually consistent. But the thing about data science, eventual consistency is okay. Relational databases, for example, will also, they have availability and consistency. But they're very bad in partition tolerance. In other words, they're not really friendly to moving the cloud on the nodes. One reason is indexing. The indexing kind of forces a relational database to stay as a big central database. So Cassandra then is your high availability now. When we talk about real-time streaming, real-time data analysis, usually Cassandra is your best bet. Akka, I told you, is the fire-breathing dragon of the cloud. Well, Akka has a way of communicating between different things. I'm not going to show this tonight, but you can do some amazing, first of all, you can do the stream up here, but you can do very interesting things by sending things to actors in the message queues and orchestrating, letting Akka do some of the orchestration there. So we have, moving this world of Spark is just starting. We're going to talk a little bit about the top stuff tonight, but it's going to keep growing and growing. Okay, eStream, I think tonight what I want to say about that is actually he takes along your little, you start with sequences. Think of it as RDB as a Spark's way of doing a sequence or collection of data. And then eStream is a whole stream of data. What do these streams look like? Well, what I'm trying to illustrate here is you're putting your stuff in batches up here. And Spark is creating these universal data representations down here all across the node. You don't really know about unless you want to. If you do flat map again, taking care of all the clusters for you. You're only writing the 2 lines of code. Spark is doing all that. So what I'm getting at is the concurrency is really powerful and it covers. You can do a save like this. You can do one save and he'll send it to all over the place for you. So again, concurrency and the cover. Sometimes too, when you have all these little data packets, sometimes you can just do sampling on it with sliding windows. Okay, so what is an RDB? Okay, it is a resilient distributed data. We just see you can live all over the cloud. You can be resilient. He knows all the different places he's got to be. He knows how to split compute splits. He uses dependencies. And it's more about interactive acrylic graph or cyclic graph, which is actually what we do in project management for PERT charts. It is the way to do dependencies. So it's very RDBs and other dependencies. And then you can do some hash partitioning and more a list of preferred locations. Okay. Let's go back here, hit the buttons. Okay. So this is what properties RDBs have for location awareness. Okay, finally, RDB workflow. Okay, we have a lot to transform. First of all, we'll load and create RDBs from the Spark context. And by the way, you can do most data science with this workflow. Okay, that's a very bold statement. But most of what you do in Spark, and if you agree with me that Spark can do most data science, I'm saying that most of everything is happening right here. So what you you do is you read input some data, load it. When I'll say you load from a Spark context, you want to do a bunch of transforms back and forth in the streams. Usually though, nothing's really happening. You're just declaring how it's going to work. The only things really happen, you can say these transforms are lazy. They won't do any computation until you start using actions to generate data. In other words, you could say, this is like the map. Nothing really happens until you do the reduce out here. So it's declarative. Okay, so we'll go back to these steps here. So the processing steps is configuring Spark and the context, loading RDDs, transforming, producing results with ANSI, and saving the RDDs and the results. Okay, Spark configuration context. Well, first of all, you remember the main singleton object? You import some nice stuff from Sparks. You say, okay, I'm going to write this one really cool streaming program. It's my main program, which will be called from the command line or other places. And he's just going to start a Spark context. And then we'll kick off the flow. The reason why I'm showing this is that if you're really writing code, you'd be writing a wrapper around this, but we're not going to show this wrapper in all the subsequent slides. Okay, step 2. Okay, how do we put data in there? Well, it's pretty simple. When we use def, we're saying that we're declaring a method. We're saying its arguments. I do a shorthand here where it's just a string, like a file path. And he's creating various, kicking off the progress. So usually, so text files, objects, everything get loaded in there. A whole text file is a whole directory of files. And parallelize will let you take our sequences or collections and convert them over to RDDs. So we can take all these input sources and convert them to our RDDs. Or if we bring Cassandra into the picture, we can actually bring in Cassandra, give it a row definition, which could be a list of column variables in there, and kick off a Cassandra RDD, which is really pretty much, the rest of the program will just see it as an RDD. And then the same thing, it's actually pretty simple to save our data out to text files or to install them back into the table. And the way you could load the Cassandra thing is you can start using SQL with the select and the where clauses. Should get back into the video camera range. Okay, transformation methods. Does this look familiar? I think it does. It looks just like a Scala sequence or collection classes, except we've just replaced the word sequence with an RDD, meaning again, we can drop functions in there to change again from the T's to the U's. We can do the flat map, and we'll see that a little bit later, how we can go from T to the sequences of U's. In other words, it's really a function that's creating this, it's permeating a bunch of possibilities, and then flattening back up into another RDD. Add filter. So really, those 3 will be your main workhorses. If you start working later on, here you can start introducing some function that'll generate keys. In this case, you can think of keys as classifiers in a lot of data science disciplines. And so you can start building some key things. Oh, something I didn't mention, and I should. Sometimes when you see these things in parentheses, that's a tuple. What is a tuple? Well, tuple is just another form of collection, whereas everything else, like sequences and things, are homogeneous. Tuples are heterogeneous. So what we're saying is we can have a key in our data in a small little structure here. So so what it says is you take a function, apply a k, and you get back just keys and data in there. Okay, we can do some set theory. Distinct would remove all the duplicates for us, and it's just one call here. In classic set theory, the intersection subtraction, meaning just, subtracting elements, or taking elements out of the set, union the Cartesian product, which you have to worry about because it can produce a huge amount of data. Sometimes in Spark, it doesn't really produce all that data. It just knows that you might be interested in doing it. And zip, which pairs up the data for you. And some sampling and piping. Now, this doesn't look like much, but what I'm trying to say is this is the building blocks of data science in Spark. Another type of RDD is when we really have, when we're doing we have a lot of classifying with keys or words, is we can start doing the groups, the reductions, joining, and even some weird relational inner and outer joins in there. So these aren't used as much, except maybe for group by and reduce. But again, good building blocks. Okay, you remember up on the chart, nothing happens until an action. So what are we doing here? We can, again, do a thing with reduce, where we can apply anything. Basically a summarization exercise, or reduce. A fold is actually the same thing, except up here we supply a little extra information and we say, this is what your zero value is going to be in there. And the rest are pretty much self-explanatory. Mins, maxes, we can take stuff out, put them in arrays, we can take out ordered stuff, and again, we can do some sampling. Not a lot. If we ever want to do side effects, like printing, I didn't mention this, you just do a for each and just say print. Print every element in there. Now, when I say it's a side effect, you see this thing unit that says return nothing, or just do something and just take it off the stream, really. Okay, then, now we're getting to near the end of the presentation, and everyone's seen this in Sparks, the famous word count. Does anybody really understand every aspect of it? I mean, what's going on at the top there? What's the first, what's inside the RDD? Is this an L or is this a 1? Oh, well, I can tell you it's an L, and that's a 1. Does it get any more cryptic than this? I don't think so. And then finally, we have these things called placeholders. Well, what we're doing is still adding 2 subsequent variables. So my contention is, everyone writes it like this in a very compact, succinct form. If you want people to follow you and understand what you're doing, code it a little cleaner. So that's what I do in the next slide. Now, what's word count about? I can actually tell you what it's about. First of all, it's not really well known, but the Spark context text file, which is our loader, and he's creating the RDD, he's actually creating lines of strings. Okay, we've got lines. Okay, what are we going to do with those lines? Well, of course, break them into words. RDD words. Again, strings. Do the flat map. Now we begin to see what flat map is doing. He takes every line, puts them in, first put them into a sequence of words, and then using this function, this is by the way a string function, this is split on empty spaces. Okay, this makes sense, at least to me finally. Okay, then, now we want to start getting into counting. And what do we do here? Well, we now have, an RDD of just all the words. It's just one big collection of words. So next step, we're going to just put a word in with it. We have to put something in to start off the counting process. So we just say take every word and turn it into a little tuple of word and 1. That is a 1. That's all you're doing. Finally, then we do reduce by key. And it's a classic reduce where he says, okay, just pair everything, just sum up everything, except sum it up by key. So we're going to have every word, and we'll have the word count and everything. And so we've done a pretty, we've parsed Done a lot of processing in 4 lines of code, and we just write it out here. And so that's actually the end of this presentation. Next couple presentations, I'll be doing a lot more examples, but decided to make it short for tonight. So references, really everything you can find to be at Scala.org. Apache Spark has the same thing. Lots of good presentations for shows. Dean Wampler's been writing a lot. He wrote the programming Scala book, which I highly recommend, but he's now working with TypeSafe, and he's doing things. He's actually, you could say, the Scala guy like me who's doing data science, except he's more famous, and I follow him a lot. And if you want to look at these slides, you can go up to my area, X in Maxim 6, and see all my slide decks. Okay, and the end, that's it. So I think we're ahead of schedule, right?
Yeah.
Okay, thanks everyone.
Questions?
Any questions? Okay. First.